This is a Total production. Hello everyone, this is going to act as our, I have it listed as our part 1 practice, but this is the first video content related to chapter 6 practice problems. And so kind of the first thing we really talk about that gets into some craziness is going to be electrophilic addition reactions. And I felt like these reactions were good in like seeing mechanisms for reactions. So where we would draw arrow pushing, where we would see intermediates, right, for the first time, and kind of showing either a product or multiple products that were possible. All right, and so in order to kind of do some of this, it's also important for us to understand the nucleophile and the electrophile, like what that is. Okay, so let's hop into it. So for each one of these, if we start with our first reaction here, all of these reactions for this page are an electrophilic addition. All right, so what does that mean? That means we're going to add something across this pi bond. All right, so that means two different things are, so this carbon is going to get something, and then this carbon is going to get something. All right, and so to understand what we're going to add, we're going to be adding this stuff associated with the arrow, this HBr, or hydrobromic acid. So how does this happen? Well, one thing is electron rich, the other one is not. All right, so one thing's going to have to attack the other. The electron rich thing attacks the electron poor thing. Well, hopefully you can kind of understand this with electrophilic addition reactions, because right, you're adding an electrophile across the pi bond. So this is our electrophile. We're adding the H and the Br, right? So one of those carbons is going to get the hydrogen, the other carbon is going to get the bromine. Right? So how does this happen? Well, you need something electron rich over here. So if this is our electrophile, that means this structure with the double bond has to be our nucleophile. So what's going to attack? Well, the only thing that's electron rich is the pi bond here. So you're going to see it attack specifically the hydrogen. Why is it going to attack the hydrogen? Because if you look at this bond, this is a polar bond where the bromine is more electronegative than the hydrogen. And we also think of acids as proton donators, right? So where's that proton, that positive charge come from? The hydrogen. All right, so we're going to see the pi bond attack the hydrogen, and then it's going to force the breaking of this hydrogen-bromine bond. And those electrons, as this arrow shows, is going to the bromine, right? So this bromine is going to get 2 electrons from that bond. All right, so let's look at what we have. That means one of these 2 carbons gets a hydrogen. So which one is it? Let's look at our structure that would evolve. So if the hydrogen went here to the top carbon, that means we would have this carbocation. All right, our other option, so I'm going to put OR, right, because we're checking our options. All right, we're shopping around. We're going to be a good steward of our money. All right, so that means so here the plus charge went there because the hydrogen went there. So now what happens if you put the hydrogen here at the bottom, right, like so, then the plus charge would now go there. So we have to evaluate these 2 options, right? These are cations, and we specifically call them carbocations. So when we look at these 2 carbocations, which one is more stable, right? And so we talked about previously, right, in terms of stability, you've got a methyl carbocation, right, which isn't stable, right? So more stable than that would be a primary carbocation. More stable than that would be a secondary carbocation, and more stable than that would be a tertiary carbocation, right? That's kind of the order of our stability. Methyl's the worst, tertiary is the best. So what do we have here? If we classify these carbocations, we see that this is a secondary, right? Because that carbon has 1, 2 carbon connections. And then this carbocation is a tertiary because it has 1, 2, 3 carbon connections. Right? So that means this is the favored carbocation. So this is going to be our major route, aka, I'm crossing that out. This will be our major intermediate, right? So this is the intermediate we would have. Now remember, this Br broke off, so there is some Br minus still floating around in here. All right, and so when it comes in, it can attack that positive carbon. All right, so in the second step here, right, because this was the first step from here to here, and so now from here to what I'm going to draw here would be the second step. All right, so let's look at our product, right? So the bromine's now going to go to that carbon. So we'd have that. All right, now, one other thing we kind of talked about here, with the tertiary carbocation, this is a trigonal planar, right? It's flat, okay? So it's like a flat sheet of paper. So it being flat, right, that means that bromine can attack from the top or from the bottom of the carbon with equal efficiency. So why is that important? Because this right here, right, that's a new chiral center. So the problem we've got here is the bromine could have a dash if it attacked from the bottom of the carbon, right, giving that ethyl group a wedge. And so the other product we've got as an option, I'm going to cram it in here, right, would be if the bromine now attacked from the top, it would have a wedge, and the ethyl group would have a dash, okay? So we have pretty much a racemic mixture of products here, right? I didn't say a racemic mixture of enantiomers, all right, but we have a racemic mixture here. All right, now if you look here, this is the same starting alkene. Our electrophile is a little different. It's hydrochloric acid instead of hydrobromic. But guess what? This is all going to follow suit in the exact same manner. All right? So you're going to have your nucleophile as your alkene. You're going to have your hydrochloric acid as your electrophile. Pi bond's going to attack the hydrogen. Right? Hydrogen can't have more than one bond, so this bond has to break, and those electrons got to go to the chloride ion. And then what are you going to have? Hydrogen can either go to the top carbon or the bottom carbon, and guess what? It's going to be the same carbocation intermediate. The tertiary one, right? That's going to be the more favored carbocation intermediate. So then your chloride ion can come in and attack that positive carbon center and give us a racemic mixture of products like we had over here with the bromine. All right, so the only difference was what halogen did we put on there, bromine or chlorine. All right, next up, here we've got HI, so it's still an acid, it's hydroiodic acid, so this is still our electrophile, our alkene is still our nucleophile, so the pi bond here is going to attack the hydrogen. You seeing a theme here? The pi bond is going to attack the hydrogen. We're going to break the bond here, right, because hydrogen can't have more than one bond, all right, and those electrons from the bond are going to go to iodine. All right, so let's look at our options here. So we're either going to have the hydrogen going at this carbon, right, like so, to give us a primary carbocation, or we're going to have the hydrogen going at the end here, right there, to give us a tertiary carbocation. And we already know, right, primary is not as stable as tertiary, so we're not going to look at that intermediate at all. Don't give me that, Clarence. All right, and so what does that mean? That means the iodide ion that we made over here can now come back and attack, right, that positive carbon. Now, in this case, I'm not going to worry about making a racemic mixture of anything, right, because if you notice, this isn't a new chiral center because that's got two methyl groups there. So I'm just going to leave it as that's my product, and I'm done. All right, next up, we have an alkene with hydrochloric acid. So remember, our acid is almost always our electrophile. Almost always. It's a very rare case when it's not. So so our alkene has to be our nucleophile. So it's going to attack the hydrogen. We're going to break the bond between the chlorine and the hydrogen. And so what does that mean? Hydrogen can either go here or here. And so if we look at it, we don't necessarily have to draw the carbocations to see. Because if you notice, what do you have here? Right? This carbon has 1, 2, 3 carbons connected, while this carbon has 2. So that tells us if we get the positive charge here, right? If we get the positive charge there at the tertiary and let the hydrogen go there, right, that is going to be our more stable one, right? Positive charge there gives us tertiary. Positive charge there gives us secondary. So that would be the most stable intermediate, a tertiary, and that's what we're going to focus on. So now our chloride ion can come in. It can attack that positive carbon. And it is trigonal planar. It can attack from the top or the bottom, but pay attention to the product here. If you notice, it's not a new chiral center because it has two ethyl groups on it. So I don't have to worry about a dash or a wedge there. All right. Okay, next up. Here we have an alkene and an acid. All right. Our hydrobromic acid is our electrophile. Our alkene is our nucleophile. So it's going to attack, the pi bond will attack the hydrogen, break the HBr bond, right? And that's going to make the bromide ion that we'll see in the second step. But now if we look, something interesting. I'm going to actually show you both carbocations. So if the hydrogen goes there, right, so that position, right, then that means we get a positive charge there. That is a tertiary carbocation. If we do it the other way, so now if the hydrogen goes here, right, so that would be this carbon right there, then we're going to have a positive charge there. This is also a tertiary. So when we look at this, we don't have a favored carbocation. We're going to make both. Oh no, we're going to have a mixture of products and not a racemic mixture. We're going to have a crazy mixture. So this is going to really blow chunks. All right, so let's put our bromide ion in here. And so I'm just going to draw bromide ion attacking that positive carbon, and then I'll show a separate bromide ion attacking that one. All right, and so based off this, what do we see? Ooh, so for that one, the product would be that product, and we're not really going to worry about stereochemistry because that's not a chiral center. It's got two methyls on it. Now, if we see this attack, we would get, there's that isopropyl and then a bromine coming off. And then from here, I don't have to worry about stereochemistry because that's not a chiral center, right? If you were to cut this in half, doesn't the top and the bottom of the ring look the same? So it's not a chiral center. I don't have to worry about it. So these would be my two products that I would get because both of my intermediates, I'll put a bracket around them, both of my intermediates are tertiary carbocations. All right, now looking at our next one here, it's a bigger structure, but if we notice, yet again, we have an alkene acting as our nucleophile. We have our acid acting as our electrophile. We would see the pi bond attacking the hydrogen, breaking the HI bond, and those electrons are going to go to the iodide. Okay, so if we look, this has 1, 2, 3 carbons connected, so that would give me a tertiary carbocation. This carbon has 1, 2 connected. That would give me a secondary. And remember, tertiary is more stable. So I'm just going to focus on writing the more stable one, the tertiary one. So that would be a plus charge there, all right, like so. So that gives me the tertiary carbocation. That also means now I've got my iodide ion that can come in and attack the positive charge. That carbocation is trigonal planar, right? It's flat. So that iodide can attack from the top or it can attack from the bottom with equal efficiency, meaning when I put the iodide there and then I put the ethyl, right there, that is a new chiral center. So I have to worry about stereochemistry. So I'll do one with a dash on the iodide and a wedge on the ethyl. Yeah, and then my other one, I'll do a wedge on the iodide and a dash on the ethyl, right? So that would be my racemic mixture. That would be my racemic mixture. All right, next up, what do we got? We've got, we kind of went simple all of a sudden, right? But when we look at this structure, we have a alkene, so that's our nucleophile. We have our HBr acid. So that's going to be our electrophile. So the pi bond will attack, right? We're going to break that HBr bond. Those electrons are going to go to the bromine, right? From there, we look. This carbon has one carbon connection. This carbon has two carbon connections. So we want the positive charge there. So that means we're looking at a hydrogen at the end and a positive charge right there. All right, from there, what are we looking at? We are going to have the bromide ion from before that broke off can come in, and it can attack that positive carbon. That is a trigonal planar carbon. So I have to worry about dashes and wedges if I make a new chiral center. So let's check it. 1, 2, 3. I put that bromine there, right? I didn't write the hydrogen from before, okay? Because they're invisible in skeletal structures. But if I look, that is a new chiral center. So I'm going to have to worry about putting a dash and a wedge. So I'll get a racemic mixture of enantiomers, because that's not a chiral center. So this would actually be a racemic mixture of enantiomers. All right. Okay, so hopefully that kind of helps with practicing our electrophilic additions, especially when it's an alkene paired with a binary acid. Adios, and stay weird.